Shall I just start then? So 2 bits. First of all, we're just about pipelines and their usage, typically, and then about reservoir types, because multi-phase flow is almost invariably related to oil and gas. It's almost invariably related to hydrocarbons that are in a reservoir with associated with oil, gas, and liquid and water all together. So as you produce hydrocarbons from a reservoir, that's really where the multi-phase flow comes. There are other situations, but it's the transportation of gas, liquid, gas, oil, and water at the same time in the pipeline, really. And it's not generally something you do. You pick to do. It's something that's convenient or cost effective. It's not a very efficient way of transporting products. So there are other examples of multi-phase flow, but typically what we're talking about here is oil and gas. So some basic processing. You've got products in the reservoir. You need to turn them into commercial products to sell. So you don't sell multi-phase flow. Obviously, you sell oil or gas, and you dispose of water. It's something you don't want. So. Single-phase flow. I mean, effectively, the analysis of multi-phase flow is an extension of our understanding of single-phase flow. Very, very important about any kind of analysis related to hydraulics and flow is how you predict the properties. Things like density, viscosity, surface tension, volume fraction, how much gas and how much oil is present at any particular temperature and pressure. And then there's really 2 sort of really considerations about multi-phase flow analysis or any hydraulic analysis. There's the temperature and pressure, basically. Some situation, if you're lucky, then you'll have a system where temperature is not important. But generally speaking, the transportation products of oil are very, very strong function of temperature. So pretty much you're always very concerned about temperature. So temperature and pressure are key considerations. There are other considerations for multi-phase flow. So that's what I wanted to cover it in the first part, anyway. So pipeline use and types. Multiple types of pipelines. Pretty much all of these exist, and we've been involved in my company's been involved in the UK. Ethylene. Ethylene is a produced by a refinery and used for plastics manufacture, and there's so much of it used it actually warrants an individual pipeline network. And there are a few ethylene pipeline networks around. There's certainly a few in the UK and also in Europe as well, transporting more material for plastic manufacture. And it does have some issues in terms of transportation, because at convenient operating temperatures and pressures, ethylene is quite close to its critical point. So you can get if you get process upsets, you can get liquid forming. So. And also it polymerizes in the pipeline, so you can get some wax deformation as well. So there are some particular issues associated with ethylene. So, and then multi-products. Multi-product means that you're effectively using one pipeline for lots of different products, but you don't transport them together. You transport them separately, one after the other. And there's different ways of doing that. You can separate them by pigs, or you can just separate them by choosing products which have similar densities. The greater the density, the more the mixing, and then the interface, which is the bit that's mixed between the 2 different products, you actually separate and then transport back to your refinery and reprocess it. So multi-products: petrol, diesel, ethylene, liquid petroleum gas, and jet fuel. So you do have to be careful transporting LPG though in multi-product pipelines, because if you even vestiges of LPG going into atmospheric tanks can create safety issues. So because LPG is liquid at relatively low pressures, so you can transport it easily in a multi-product pipeline. But if you then transport it, typically multi-product pipelines go between tank farms. If you then put LPG into your tank, or vestiges of it, you'll get gas forming and potentially some safety issues. So, Moni? Jet fuel. Most large airports have permanent pipelines connected to them. Heathrow certainly does, because if you actually work it out, you'd end up with literally hundreds and hundreds of tankers every day arriving at your airport. So. Morning. And then gas, obviously. There's the dry gas that's transported in the transmission system. We get the national transmission system in the UK, for example, as a domestic product and industrial product. But also gas, wet gas within fields as well. Oil, obviously. Water, LPG and condensate, liquid natural gas, which is at incredibly low temperatures. And atmospheric pressure, and then multi-phase, which is one of the main topics we're going to be talking about. So, lots of seats here as well. So, a few examples. This is a liquid LNG jetty. LNG is produced by using a cryogenic process to liquefy gas, so it's transported at about a minus 170 degrees centigrade typically, and atmospheric pressure. So it's stored by putting it in very insulated containers. So you have ships that sail around the world which are very, very highly insulated, very expensive as well. And you have to use exotic materials because you're operating at minus 170-ish. You'll find that conventional carbon steel is very, very is not tough at that temperature, so you end up using expensive nickel-based alloys that maintain their properties at these very low temperatures. So you store it in insulated containers, you transport it in insulated containers. These are insulated tanks, and this is the loading jetty. So this is an LNG pipeline. They are very rarely subsea. There are some examples of subsea LNG pipelines, and sometimes they are onshore. But the typical features of an LNG pipeline is it has a huge amount of insulation, because as that product heats up, it loses gas to the environment, basically. So there's a big cost benefit in having a lot of insulation. Also, if you install this at an ambient temperature, say it's 10 or 20 degrees, I think this is in Trinidad, I suspect, and then it operates at minus 170 degrees, then you get an incredible contraction and tension forming. So not only is it a heavily insulated pipe, but also it has potentially an enormous axial load. So you put these loops in to stop it effectively generating a very, 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 very high tension. So that's a very special case, an LNG pipeline. Sometimes they are buried. You get onshore LNG pipelines. There's one in India at the moment. I know they're constructing right now as we speak. There's a subsea one in Peru, but normally they're like this on jetties. So. We talked about the ethylene pipelines. This is the UK ethylene pipeline network. It's lots of four-letter abbreviations. That's Northwest Ethylene Pipeline, Teesside to Saltend Ethylene Pipeline. Not sure what RCEP is. So it's transporting basically ethylene around from refineries to manufacturing plants, basically. So. And fuel hydrant systems. Once the jet fuels arrive at the airport, there's whole networks of distribution. And this is the basic system that's underneath Terminal 5. And this is all underneath the runways. So you're probably aware runways are something like a metre thick of concrete, massively reinforced concrete, to take the load of these huge aircraft landing. So a lot of this is underneath the runway, almost impossible to access, and it pops up at these hydrants every now and again. So jet fuel would arrive at Heathrow. It has settling tanks. It's left in a tank for a few days before it's used, and then it's distributed around the whole airport under a constant pressure system. So this is Heathrow. You can see Terminal 1, 2 and 3, which are the old ones. Terminal 4, I think of it as new, but it's about 20 years old. And then Terminal 5, which is about, 5 years old or something. So So that comes from a refinery, and there's multiple providers and multiple users of jet fuel at Heathrow Airport. So. But from a hydraulics point of view, jet fuel is relatively straightforward. It's benign from a corrosion point of view. It's easy to analyse. You can do it. You can almost, to be honest, you can do it on a spreadsheet. I was doing it yesterday, in fact, on a spreadsheet.
What are the pressure ranges for the jet fuel transmission?
Very low. It's just like 20 bar or something. I think it depends. Yeah. So yeah. All you got to do is get it. They have a hydrant and they connect onto it and then connect it to the plane base and get over the valve. So the alternative method was these Bowsers, they call them, which is like a truck full of fuel. But it's very impractical for a very large busy airport. So yeah, so they operate at relatively low pressures really. So and they're very hard to maintain. That's the problem with that's the thing about jet fuel lines, because it's under this solid concrete basically. So yeah. This is a pipeline I was involved in. It's an export. This is a typical oil export line. This is the Clare field, which will be described as west of Shetland. And it's got an automatic slide advance on this one. These are, we call them trunk lines, which is exporting from the field to the. I must get rid of that. Field to the terminal. And these are all the various routes we considered. When it came to it, none of these options that cross the island were actually acceptable from an environmental point of view. So this is the one they went for in the end. And even individual anchor placements of the lay barge were considered to be environmental issues. So they were planned and they looked at the environmental impact of individual anchor placements within this. I think they call it the Yell Sound. So it's it's actually a very high viscous crude, but from a hydraulics point of view, it was actually quite straightforward. It wasn't even insulated. It was ready for it at that time. So that's the Clare field. Been operating for many years now, and there's a number of other fields around here. Schiehallion is one of them. Clare's a BP field. This is a conceptual pipeline system in Japan, and we were involved in the survey of this. And the idea was it was taking gas from Sakhalin Island and then transporting it all around Japan. And because it's so congested and mountainous, they figured out it's actually easier to run the pipeline around the outside to the various cities than it was to actually run it on the shore. So it's basically taking gas from Sakhalin Island, which you probably know is a gas-rich island. Japan has no natural hydrocarbons present, so it imports from LNG. This is a way of getting gas to Japan, and then a series of loops around distributed to the various cities. So interesting project. I'm pretty sure it hasn't gone ahead, but massive investment, of course. So this is the survey boat. I think someone told me there's a dog here somewhere. Yeah. There. Yeah, someone sent me an email and said, "Do you realise there's a dog on your picture?" It's pretty unusual to have a dog on a survey boat, so the mascot, I suppose. I'd like to think it wasn't their lunch, but this is a very challenging pipeline between Judy and Jade. It was an incredibly high operating temperature and pressure. I can't remember precisely, but I think it's something like 150 degrees centigrade and like more than 10,000 psi, and waxy and hydrates as well. So it has to be transported between two platforms, and it was multi-phase flow as well. So this is one of the most challenging pipelines I think you could possibly imagine. It's got everything in terms of issues. So it's incredibly highly insulated. It cannot allow the product to drop down below something like 20 degrees because you get hydrates forming. Probably get waxes forming at 35 degrees. So it's very, very heavily insulated. You'll see later the only way you can get, for a subsea pipeline, the only way you can get a very large amount of insulation is to have what we call a pipe and pipe. So it's a steel inner pipe, obviously, and then the outer pipe is also steel, and then you have a very, very, in the space, you have a vacuum or very low pressure, and in that vacuum you have a very, very good insulator. Because good insulators are not mechanically strong. So to be able to build a pipeline where you have an insulator which is conventionally installed, it's quite difficult. So when you want a very high amount of insulation, you have to go to a pipe and pipe. So this is a pipe in pipe system. And obviously it generates, because it's very hot, it generates enormous axial loads, and the way they deal with that is to put all these individual spools in to accommodate the thermal expansion. So it's quite a robust solution. So this is the opposite situation to the LNG line. It's very hot as opposed to very cold, and these are to remove the very high level of axial tension. So very challenging pipeline, very expensive, very critical. So some years earlier, an operator tried a technique of allowing lateral buckling or snaking. I don't know if you've covered that in any of your lectures. Effectively, they laid the pipeline in a snake formation, and then operated it and allowed it to actually move across the seabed, but it failed catastrophically because the snaking configuration that they planned on putting in actually didn't actually concentrate the buckles. They all went into one large buckle rather than lots of individual movements, and that buckle actually failed full bore. So they got full bore rupture basically in their pipeline. So this is kind of an antidote to that problem. It's very expensive. You can imagine a lot of construction, but it's fairly robust from an engineering point of view. So I think that the dealing with lateral buckling is a little bit more advanced now. And I think there was a project called SafeBuck, which was I think it was about 10 years ago, which looked at this lateral buckling phenomenon and came up with safe methods of actually allowing lateral buckling. So it's very challenging pipeline. Definitely lots of multi-phase flow issues related to this. So the area where I've applied multi-phase flow the most, and most of my experience from a pipeline point of view is in the North Sea. Another one. This is a very typical North Sea development. It's got an FPSO, floating production, storage and offloading, where it collects the hydrocarbons, and it has a number of drilling clusters around it. These are accessed different parts of the reservoir. In fact, it's got 1, 2, 3, 4, I think. So West Drill Centre, North Drill Centre, North East Drill Centre, East Drill Centre. Now there's a manifold in the middle of one of these, and it collects the oil from the various wells. And then the wells produce back to the FPSO. The gas is separated, and there's a gas export pipeline. You can just about see it here, going to a hot tap T into an existing gas line. I think that's Shell's Guillemot line, I seem to remember. So, and this is a dedicated manifold for water injection. With some reservoirs, reservoirs will produce naturally for a few years, and then slowly the oil pressure will reduce. And a method of actually enhancing the production from the reservoir is to actually inject water. So typically you inject as much water as you inject oil, and you remove oil, or you inject more water than you remove oil, and that will maintain. And it's also possible to even boost the reservoir. So in fact, if you don't do that, you might find the whole seabed will start to settle and move down, which is what happened on the Ekofisk field, which is in the Norwegian sector. The whole field started to move down to a point where the spider deck of the platform actually ended up being close to the water, and they had to jack up the platform at vast costs. So injecting water is a critical aspect of hydrocarbon production, but also it can avoid the situation of this settlement as well, potentially. So the pipeline clusters going from these manifolds to this FPSO typically work on a multi-phase flow regime. So because you're getting well products here, and then you produce this will be processed here. The tanker will connect, and then you will send off produced oil, which will be at low pressure, very low vapor pressure, and the gas is exported down here. So typical North Sea field, I would say. FPSO is used because of the water depth. If it's in the southern part of the North Sea, you probably build a series of platforms, but the economics of an FPSO become more attractive in the, in the deeper water because of the cost of, imagine the cost of producing jacket platforms in all these locations. One big mega platform and drilling all of these separately with directional drilling is a possibility, depending on the depth of the reservoir. So this is probably probably the most economic solution for that kind of field in that water depth. So
Question.
yeah.
How long does it take to fill the FPSO in such cases normally, and for the next one to come in?
It depends enormously on the production, obviously. But when I worked offshore, the field I worked on, it was about 10 days to fill up the tanker, basically. Obviously, it depends on the tanker as well. So.
And the next one is ready for the...
Yeah, because you can't, you can, this has some storage in itself, so it can produce without a tanker, but very quickly this gets full up and you need to produce it into a tanker, basically. So often you see them, the tanker will be down here, basically. Yeah, so we talked about oil flowing from subsea manifolds to platforms, and these are typical configurations. If you take a cross section of all those pipelines flowing from a manifold to the FPSO, this is what typically what you see. Okay, and the oil or multi-phase flow and gas, basically, I would say. So normally you have a production line, an insulated production line, and sometimes you have a little line connected to the top of it as well, called a piggyback line. Now that piggyback line typically is used for gas lift. Gas lift is another production enhancement technique. It's for reducing the pressure drop in a well. And the way it works is it actually injects gas at some point below in the well bore, and that aerates, in fact gasiates, if that's the word. That intentionally creates multi-phase flow in the well, and reduces the density of the fluid by introducing gas. That allows the well to flow more effectively. So I would say typically in the North Sea and other fields around the world, you have water injection to maintain the reservoir pressure, and then you have gas lift to actually reduce the pressure drop in the well bore. Because in a hydraulic system, if you consider going from the reservoir, the perforations in the bottom of the well tubing to the separator, sometimes the most pressure drop actually is in the well tubing. So if you think about multi-phase flow, it's not just in the pipeline, it's actually in the well tubing. And with deep reservoirs, you might find that's where most of your pressure drops taking and your temperature drops taking place. So gas lift. Gas injection is the other technique, and it's possible all three could be used at the same time, basically. So that's our production line with our piggyback line. This is a test line. The reason why you have a test line is because it's very important to know how each well is performing. So if you have multiple wells, so the idea is you produce from one well on its own through the test line, and that goes to a separate test separator. And then the test separator will give you the oil, water, and gas coming from that specific well. That will allow you to manage the production from your field. So you can tell the difference between the different wells. Other ways of doing that are to use subsea multi-phase flow meters. So it's possible you could dispense with that pipeline by having a flow meter. The other potential technique is to shut one well down and then look at the difference. In other words, look at how much product stops. That's sometimes used, but obviously you're reducing your production if you do that. So test is often a requirement. And then you've got a water injection line. So you've got so in terms of wells, you've got two functions. You've got a production well and a water injection well. Gas lift on the oil well. Water injection is a dedicated well. And then you've got some kind of control functionality, because you need to measure you have to measure annulus pressure in the well. You have to measure production pressure, production temperature. You have to have control functionality. You have to be able to operate the various valves to separate the flow to enable you to do the testing. So they're the three main sort of lines, and then you've got other lines, potentially gas injection, water wash quenching, another example. Water wash quenching is where one technique for dealing with incredibly hot products or very saline corrosive products is you can actually run water to the well and mix it to reduce the temperature. So that's one possible strategy basically. And the other one is there may be from time to time you'd want to over pressurize the reservoir with water to I think similar to fracking. You overpressurize the reservoir with water to actually enhance the production. Now, because of these lines are relatively large diameter, you may not be able to actually derive enough pressure using these lines, so you have your own specific line for that function. They call it scale squeeze, so typically a smaller diameter, thick wall line for producing a very high pressure into the reservoir. So that's oil or multi-phase flow lines. Then gas, same, you've got the production and the production, and you've got test. Here you've got a piggyback line, but it's for a different purpose. You've probably heard of a thing called hydrates. If you're producing from a well, gas typically is associated with water. But if you have gas and water together at high pressures and low temperatures, it falls like a solid, a bit like ice. And the only way you can deal with that, in a well situation, obviously you can't separate the water. You know, it's subsea, you've got no real way of dealing with it. The only way you can actually do it is to inject methanol at the well to enable you to actually, it's a bit like a antifreeze to prevent hydrates forming. So you often find this piggyback methanol line. In fact, it's methanol glycol. There's a few different chemicals you can use to prevent hydrates forming, and this becomes saturated with water because it comes back to the platform in with the gas, of course, and then you can remove the water by boiling it off and recirculate it, send it back to the well. So it's a cyclic process. So that's the other line, and then of course the control, chemical injection umbilical as well. Same thing for the gas. So any questions? Am I going about the right speed? Yeah. So if I go too slowly, it'll take forever. So. Bundles. So have you looked at bundles at any other parts of your course? So okay. You'll see with a lot of fields, a lot of offshore fields. This is predominantly related to offshore pipelines. You'll see there's a lot of pipelines between platforms. You know, you might have a whole collection of pipelines between platforms with different functionalities. Now, the typical construction technique is to go out there with a lay barge and lay them all individually backwards and forwards. If the length of those flow lines is not that long, 6 kilometres, typically 3 kilometres, one technique which is used is to produce a bundle of pipelines. So what you do is you actually, on land, you actually create this bundle. So you have spacers, and then you weld all these lines up, and then you pull it into this carrier, and then you weld up the ends, and then you actually tow the pipeline to the site, sink it basically, and then tie it into the rest. And it's an alternative construction technique. So a lot of pipelines in the North Sea were actually installed using bundles. And in the Gulf of Mexico as well, they've used these bundles. Typically in the North Sea they use this mid-depth tow technique. So it's towed where it's hanging in the mid-depth, in the water column basically. And in the Gulf of Mexico they've got this another technique they call the bottom tow. They actually drag it along the seabed to where they want it. That's been used. So this is a bundle. So from a process point of view, the topic today, it allows you to add lots of insulation. It also allows you to actually heat this pipeline bundle with hot water. So you can actually run hot water inside the bundle, heat it up on the platform, run it down inside the bundle, and then return it and then recirculate it basically. Now there's at least one field in the North Sea which works like this. So they actually use circulated hot water to maintain the temperature of their product. So trying to think of the name of it. Britannia, I think is the name of the field that uses this technique. It's got a number of bundles, and it circulates hot water to maintain the product. And the reason why you're maintaining the product temperature is to avoid hydrates and wax. So, yeah.
How do you install valves and some fittings on this kind of?
That's a very good question, and yes, you can. Yeah. They've installed these bundles with massive manifolds on them. Yeah. They've installed them with subsea isolation valves halfway down. They've installed them with massive manifolds on both ends. Certainly, it's quite usual to have a skid with all the flange connections on the end. So yeah, no, you can put. It's like a submarine basically. So you can put a lot of equipment on it. It seems very elaborate. It seems very elaborate and expensive, but the reason why it works is because you're doing all this onshore. Because you're building this complicated structure onshore. Whereas the alternative is if you've got very expensive equipment offshore, divers, dive support vessels, lay barges, very, very expensive, very complicated. And whereas here you can do it all in your own time, with conventional welders, and then you'd limit the offshore work. That's the reason why this technique's attractive from a field development point of view. So, and it's not obscure. It's been used many times. It's not obscure. I mean, I don't know how many there are. 20, 30 of these in the North Sea, for example. So,
what are the minimum and maximum diameter sizes?
These can go right up to. I've certainly been involved in like 36 inch, 38 inch, 40 inch. So yeah, big, really big.
What about corrosion?
You're talking about external corrosion on this is never a problem because you've got anodes.
Yeah.
The internal corrosion of the pipelines is the same as it would be for a normal pipeline. The outside of these pipelines typically are. This is in an inert environment, so you can put. I would say typically a bundle, they flood it full of water, but it's inert water. It's been treated, so it's got corrosion inhibitor, oxygen scavenger in it. It's a completely inert environment. So it's sealed, so there's no transfer of fluids. So corrosion's not really been a problem. If you get corrosion on the inside though, then there is a problem. Because the problem with this technique is obviously accessing these pipelines. So if you want to do a subsea repair, for example, due to a corrosion issue on the inside, I agree that's an issue. So one of the downsides of this, of course, is access after you've installed it, basically. But that's unusual, to be honest. You use it in a situation where you feel you can manage the corrosion. And often you'll find the pipelines inside bundles are corrosion-resistant alloys. Some of the ones I've worked on have been using stainless steel for the inner lines, so again, very expensive. So,
would the carrier pipe be watertight, or would it just be as a protective barrier around?
The carrier pipe is actually an integral part of the structure because it resists the very high axial load produced by the pipelines, potentially at high temperatures. And it's full of air during the installation process, so it's like a composite structure. So yeah, it does take quite a lot of stress actually, and then they sink it, and then the thing is lowered to the seabed and flooded basically.
Okay.
So with inert seawater. So yeah.
Is it possible to run peak inside the production?
Yes. As far as the pipeline is concerned, it doesn't even know it's inside a bundle. Yeah, there's no real. It's connected with conventional spools. So from the inside point of view, the pipe is like any other pipe, basically. Yeah, absolutely no problems running the pig. You can't obviously run a pig in any of this stuff, the annulus. But that's full of inert water. So.
I can't really visualize how do you store the whole bundle again. Say you're doing it offshore, you bring the whole stretch.
It's made up on. I wish I had some pens. Don't have any. Okay, they make the whole thing up on land, and it's on a trolley system basically.
Oh.
So they pull it out. It's got chains on it as well, and they pull it out offshore. So it's at this stage, It has a very low submerged weight. So then you could hold it between two tugs. So it's suspended between two tugs like that. And then you tow it slowly to your site. When you get to your site, you can actually lower it down onto the seabed. And it's got this like off seabed mode. You can actually, it's suspended above the seabed on chains. And then you can move it around on the seabed by pulling it. When you get it exactly where you want it, you flood it. And you sink it basically. And then you, at the end, sorry, is that it?
Yes, I'm Sharon.
Oh, I thought you
Sorry.
wanted me. Yeah.
Just if you want to use the visualizer to sort of write down.
A visualizer.
Yes, just like instead of the whiteboard,
Uh-huh.
you can change this in here to this one.
That's amazing.
Like that, and
Yeah.
then you can write down in here anything
Okay.
you'll need. And then if you want to come back, you just go back
Thank
to
you.
the PC.
That's
Okay,
thank
yes.
you. Fantastic. Ah.
Oh yes, I went to PC, but I think your
Oh no,
case
it's laptop.
is to the
It's laptop. Yeah.
Yes,
Okay, that's
the
what it was. Yeah. Okay. Thanks. No, I'll do that next time. Yeah, that's a good idea. So, any more questions on the bundle?
Yeah. The pipes are made of different pipeline material, and if that's the case, do you have like galvanic corrosion?
Yeah, that is a consideration, definitely. Normally you try and make them carbon steel because that's the cheapest. But sometimes sometimes they are stainless steel, yes. And then you have to basically join carbon steel to the end. The end bulkhead is a very complicated thing, as you can imagine. It's normally a forged piece. The fitting at the end, which all the pilots fit into. So there you've got to join stainless steel to carbon steel. So you have like a buffer layer. You need some very careful considerations about metallurgy. That's right. On the inside of the bundle, you've got this inert environment. So, but yeah, you're right. That is something you need to be careful about for sure. So, a lot of interest in bundles, which is good. There's examples of again multi-phase flow. This is Shell's Mensa field, which is in the Gulf of Mexico. And at the time, this is one of the longest. The thing about multi-phase flow is it doesn't go. You can't go very far. I mean, the rule of thumb is 20 kilometers because it's very inefficient. It just runs out of pressure basically. Whereas this one is 140 miles. Hold on, there's 140 miles. I can't remember. Say 63 miles basically. And the reason why they did this is because this part is in incredibly deep water. So the question is, and it's not a particularly large field, so to have your own deep water floating, FPSO is not economical really. So the advantage here is if you can flow it all the way back to a platform, then there's a big advantage. But then to do that, they had to go 63 miles, which is way beyond what you could normally do with multi-phase flow. But because there's a relatively small amount of liquid, it enabled them to actually do it. Go back, run it for 63 miles to back to the platform. Because there's only about a few barrels per million standard cubic feet of gas, so not much basically. So, and it's in 1,600 meters of water. So it's a completely remote field, effectively. Long distance tieback, I think, would be the term you'd call it. So, and this is the Mensa manifold. I don't know if you've studied deep water fields, but they, you can't use conventional divers at all, so they have to use these made-up spools with vertical stabbing connections. So you'd lower something like this down to the seabed, and then you connect each well individually with these lowered in vertical stabbing connections. So at the time, it was the longest tieback in the world, 109 kilometres. So. Example of a multi-products pipeline. I was actually in Malaysia a couple of weeks ago, but this is taking it from Klang Valley to Malacca, basically. Malacca's you probably know, it's a big port. So 145 kilometres, 16-inch pipeline. So through palm oil plantations. So this is the Blue Stream project. A sort of extreme example. From a process point of view, this is not really a big deal. This is you think it would be, but this is going across the Black Sea, and it goes down to 2,150 meters of water, 380 kilometers distance, and you can see what the profile looks like. Going down to 2,000 meters, but actually it's fairly straightforward from a process point of view. The challenge here is materials and construction in very deep water. And actually, there were some issues with concern about hydrogen sulfide in the soil as well. They were worried about stress cracking, corrosion on the outside of the pipeline. So the least of the worries really were process on this particular project. So okay, this is an example of how things might change in a particular environment for a pipeline. Whatever particularly if you're building pipelines in an area which is subject to, which has lots of surrounding fields, different complicated ownerships, and you'll find like for example the shale gas in the US or offshore the Gulf of Mexico, offshore North Sea, lots of owners, lots of changing ownership, lots of complicated marginal fields, complicated structures, limited infrastructure to actually import it. You'll find that how you envisage your pipeline originally could be radically different, different in the future because of all the different surrounding factors. So it's an example of that type of situation. This is the Forties field. This was developed by BP. It's one of the early fields in the North Sea. This is how it looked from 1973 to 1983. This is the Forties Charlie platform. Central processing facility, had 3 satellite platforms, producing oil through one 32-inch sea line, and it had 2 pumping stations to a refinery, and there was an offload only shift to a platform basically. So challenges there were increasing Forties production, producing water and produced water slugs with pigs basically, getting water out of the line basically, because that's obviously creates corrosion issues potentially. These are mainly BP fields. But between 1983 and 1992, you'll see that now we've got a whole multitude of different fields tied back into Forties Charlie. Most of those are actually BP. I think nearly all of them. I think maybe all of them are BP fields actually. So still got our 3 platforms though, and Forties Charlie. Challenge is now we've got CO2 and H2S contamination. Because the interesting thing here is, of course, whatever you considered about this original field, you only considered a product from this Forties reservoir. Now you've got all these other fields producing into it with different reservoirs, different compositions. So suddenly you're getting issues that you weren't expecting potentially. More gas to deal with. Variable feed compositions, so that the composition is changing here. Hydrocarbon counting and metering. How do you take account of all these different? Because some of these fields may not be 100% BP. So how do you meter? How do you meter the fields to determine whose product is what, and to satisfy your agreements with your partners? Between 91 and 2000, something becomes incredibly complicated. And these are lots of different operators. These aren't all BP now. Some of these are Total, all sorts of different operators involved, all tied back to the Forties field, and even they built a new platform even. So still operating through the sea line, 36-inch sea line. By this time, this pipeline was producing about 1 million barrels a day. We're going through this pipeline. It was one of the most prolific pipelines in the world. One of them. And they had to install additional pumping stations, and they installed another loading terminal. So if you look at the forces, you'll see this blue area is the Forties field, And you see by now, Forties are producing almost nothing at all. In fact, it's not even owned by BP anymore, it's owned by Apache. In fact, I'm not even sure Apache have it anymore. I think they divest. I think they don't even actually have it now. So they divested in it, basically. So this is all the other fields, and this is future business. So the original Forties pipeline is no longer a pipeline for Forties field. It's now a general trunk line producing from many other fields. And all its original Forties production now is pretty much gone. What I'm trying to demonstrate really is that when you think about the design of a pipeline, particularly in this very congested sort of area, then you've got to be extremely careful about how it might be used in the future, because it becomes an incredibly valuable investment for everybody else to use. So it's the same for any other pipeline of this sort in this area. So that's variation based on a business case, and the other the other one thing I want to talk about is just uncertainty. Uncertainty. This is again from BP data, and this is a chart. This axis is spend, so that's 80% overspent and that's 40% underspent. And this vertical axis is production in terms of expectations. So that's 60% overproduced and that's 100% underproduced. So if you're designing a system, you have to consider that what is predicted to happen may not actually happen. So for example, Foynhaven, I think this is in its first production year, was like 100% less than they expected in terms of production. Andrew was 40% more than they expected. So you do this very detailed analysis, and if you actually talk to reservoir engineers, they'll tell you that actually, pretty much what you're working on is kind of a guess. It's our best estimate. So you really can expect some variation. It's not an exact science. So if you take account of this plus the previous slides, when you're designing a pipeline, you've got a lot of potential things that might change in the future. So. How are we doing for time? 9:52. Okay, so we said before that pretty much most multi-phase flow you're likely to come across is related to hydrocarbons, and a reservoir is really it's like the source, if you like. So there's different sorts of reservoirs. Solution gas drive, sometimes known as pollution drive, depends on the associated gas of the oil. The virgin reservoir may be entirely liquid, but it has hydrocarbons in solution due to the pressure. As the pressure in the reservoir goes down, the pressure falls below the bubble point. The bubble point is a property of gas in situ, basically. It's literally what it says. When you go below that pressure, bubbles start to form. You start to get gas coming out of the fluid. It's a bit like undoing a top of a fizzy drink, basically. Reduce the pressure, gas comes out. And that's actually a strong function of temperature as well. That property. So gas comes out. As the reservoir depletes, the pressure falls below the bubble point, and the gas comes out of solution to form a gas cap. So you'll find that the oil will move down in the reservoir, and you'll get this gas cap forming, and that's acting like a big spring. So that continues to push on the liquid and allow that to be drained. It's like a big spring. Because if you didn't have that gas in the reservoir, in the oil, obviously there'll be no gas coming out, and you wouldn't get an increase in pressure. So your reservoir pressure would very, very quickly deplete. So that's actually a good thing. It's allowing you to continue to produce from the reservoir. So natural water drive, black oil. So you see there below the hydrocarbon, you've got a big porous reservoir. Oil floats on water. You've got a massive reservoir of water. with oil sitting on it. Now the volume of that reservoir of water can be enormous. It can be as big as a country. You'll find that big swathes of Libya, for example, have got this ancient aquifer of water. So you'll find that in terms of volume, your oil volume is very small compared with the water volume. So as you remove the oil, your oil just gets replaced by the water. So you've got no real issue in terms of drive. So the groundwater, the water, as with all liquids, is compressible to a small degree. As the hydrocarbons are depleted, the reduction in pressure of the reservoir gas causes the water to expand slightly. Although the expansion is minute, the aquifer is large enough, this will translate a large increase in volume, which will push up the hydrocarbons to pressure. So these are both good, very good things. So the water expands slightly, pushes the oil out, gas comes out, solution pushes the oil out. So gas cap, volatile oil, this is where the reservoir already has a gas cap. It already has a gas phase and a liquid phase in the reservoir. So in other words, it's already below the bubble point. So the gas cap expands with the depletion of the reservoir pushing down the liquid, forming extra pressure. So you, in that type of reservoir, you can actually drill into different bits, and so you can produce gas from some parts of the reservoir, and you can produce oil or multi-phase flow, or oil from other parts of the reservoir, or multi-phase flows. So reservoir fluids. So in terms of what you find in reservoirs, you get the hydrocarbons ranging from methane, CH4, to very, very high molecular weight components, complex, 40 plus atoms, and then you've got all the variations of those as well. So it's actually a very, very complex organic chemistry. 4 principal types of hydrocarbons: paraffins, saturated or straight branches or chains, naphthalene, saturated cycloparaffins, olefins, and aromatics. The low C numbers, C1 to 5, is effectively a gas at atmospheric conditions. So these are effectively what you could think of as gases. And crude oil is the C6 plus, basically. And they typically contain contaminants as well. So this is what you typically find in a reservoir in terms of hydrocarbons. Also, you get things you don't want as well. Certainly, water is very, very common. Very, very common indeed in whether it's gas or oil. Water is typically there. Often, that water is completely saturated with salts, and those salts can give you corrosion problems and also scaling problems because they're saturated because the water is saturated with salts. When you reduce the pressure and the temperature, they come out of solution. And when they come out of solution, they can actually form solids. Now, if that solid forms as like particles in the water, then it will just be transported out of the reservoir. Is not really a problem, or out of the pipeline. But sometimes they form solid scale on the inside of the pipeline, which can completely block the flow. So scaling is a potential problem with salts in water. There's acid gases, which can actually cause corrosion in your pipeline. I'm sure you've covered this in other lectures, but the CO2 is one, and H2S is another. CO2 causes corrosion. H2S, in some situations, can actually help with corrosion, but obviously has other issues. Hydrogen cracking, for example. Hydrogen-induced cracking, HIC. It's very nasty for materials. So these are things that are not good. There's no real important use for those things. They're contaminant. You could treat them as unwelcome components within your hydrocarbon stream. So solids, such as sand, you'll find that these are the reservoir. If it's a sandstone reservoir, you'll find that you'll get in some reservoirs you can get sand produced. And the problem with sand produced, it ends up in reservoirs. Sorry, it ends up in separators. Quite hard to deal with. So sometimes you have to shut the separator down, enter it, and dig out all the sand. but also you can get erosion as well. Whenever you get a bend, you'll get the sand particles impinging on the bend, and it's actually possible to actually cut right the way through a bend. So sand is not good. And you'll find on some gas plants, you'll find these things called sand detectors. So it uses an acoustic method to detect sand production. Because you might have downhole screens to prevent sand production, but the problem is that they can fail. They can become overpressured. They can actually rupture, and then you get sand being produced into the reservoir, and that could quite quickly damage your equipment, damage chokes, damage elbows, cause failures, create safety issues. So the idea of the sand detector is that once you pick up the production of sand, then you'd have to actually shut that well down and fix it, basically. So it's a safety critical thing, a sand detector. So sometimes you get inert gas. You often get a little bit of nitrogen N2, but some fields have got a lot of nitrogen, and it's not obviously the air is full of nitrogen. It's not harmful in any way. It's just not worth anything. So it's going to reduce the calorific value of the gas. You have to get it out, and it has no value. So, and in terms of oils, you can get heavy metals, vanadium, zinc, mercury. These are undesirable. Some of these can have very undesirable effects to downstream processing. For example, vanadium. Vanadium, I believe, can interfere with the catalytic processes. So, sulfur is another one again, which is something that's not desirable, treated as a contaminant. It doesn't have any benefits. You just want to get rid of it, basically. So, any questions?
Among the contaminants is CO2, carbon dioxide. But we also know that some fields are produced for enhanced oil recovery. You can use CO2 for.
Yes, that's right. Yes.
So
yeah.
is it like a trade-off?
Yeah, swings and roundabouts. If you pump loads of CO2 in, then you might increase the CO2 coming out. Now, CO2 and water produces carbonic acid, which is a corrosive to a pipeline. So, yeah, you're right. CO2 is used as a product enhancing technique, but then it may enhance your corrosion issues. You can work out the partial pressure of CO2 if it's more than a certain amount. I think it's 5 bar. Or 20, I forget. There's a simple formula for working out corrosion rate of CO2, so you may end up having to inhibit or even use exotic materials. So yeah, it is a trade-off, definitely. So, yeah. They use in Mexico. They use nitrogen as an enhancement, production enhancement. In the Cantarell field, they've got a massive nitrogen plant on shore. When they create nitrogen using a cryogenic process, taking it from air, and then pump it offshore, and then put it downhole to enhance production. So in nitrogen in Mexico. So. But you're right, they ship nitrogen around the US and use it for enhanced production. So, in fact, there's a company called Kinder Morgan that have a business in transporting CO2 for that purpose. So, so this is very important. This is kind of the crux, really, of multi-phase flow. So. We call this our hydrocarbon phase envelope. And inside the envelope, we've got multi-phase flow. So we've got two phases occurring at the same time. So here we've got pressure. Here we've got temperature. So you can, if you think of a hydrocarbon product, you can plot where you are at any one point on this chart. And there are 3 different composition products being represented on this chart. So this one here is a gas condensate. This dotted one here is a volatile oil, and this dotted one here is a black oil. And you will see that the shape of the hydrocarbon phase envelope changes depending on the composition. So it goes further to the right. You see that this little thing with C? I'll explain what it is in a minute. Moves to the right. So the shape changes. So this is plotting this out and knowing where you are on it for a hydrocarbon is very important. So now you get lines of. So if you, for example, if you're here. You've got effectively oil in a reservoir. When you reduce the pressure, see this is reducing pressure, and you hit this line here. This is called the bubble point. You start to get gas coming out of solution, and these are lines of constant volume. So that's 100%. This is 100% liquid. This is 80% liquid, 50% liquid, 25% liquid, 10% liquid, 0 liquid. And these all converge on the critical point. So if you imagine that you're at the critical point, tiny variations in temperature and pressure will give you all switch between 100% liquid, no liquid, 10% liquid, 20% liquid. So operating at that, probably operating close to that, is probably not a good idea. You're going to get very unpredictable phase behaviour. So that's the bubble point, reducing pressure. And then here, the dew point, reducing temperature, hits that line. That's 0% liquid. Then you've got 10% liquid. You're starting to get droplets of liquid forming, basically. So they call that the dew point. And where they meet is the critical point. So there's a feature of this phase envelope, which is interesting. Which is this region is called the retrograde region. This is actually a dew point. You see, this is the 10% liquid line, which meets there. This is the 0% liquid line, meets there. So if you're here reducing pressure, your oil and your liquids forming. But if you're here reducing pressure, you get droplets of gas, droplets of liquid forming. So they call this retrograde condensation. So reduction in pressure gives you liquid coming out, liquid forming, basically. You see, you don't get this effect on volatile oil, black oils. You only get in gas condensate. So they call that the retrograde reason. Retrograde is like upside down. Because normally, if you think about normal single, like binary fluids, simple. When you reduce the pressure, liquids disappear. Whereas in this situation, you reduce the pressures, the liquids appear. So it's the other way around. Basically. That's why it's called retrograde. Retrograde condensation. So if you think about a reservoir, you've got a well tubing, you've got a pipeline, you've got a riser, you've got a separator. You've got changes in temperature and pressure. Typically the reservoir pressure might be 100 degrees centigrade. By the time it gets to the platform, it might be 20 degrees centigrade. The reservoir pressure might be 200 bar. By the time it gets to the platform, it might be 50 bar. So you might start up here somewhere in terms of temperature and pressure. So as you go down the well tubing, go down the pipeline, you drop down into here, you get condensate forming. That's where you hit multi-phase flow. That's the significance of multi-phase flow. But it's quite possible you can pop out the bottom. So it's quite feasible that you can have multi-phase flow in the pipe. You can have single phase in, multi-phase flow in the pipeline, and single phase out. I've actually come across that before. So it's very inefficient, but quite perfectly feasible for that to happen. So often gas condensate systems, you're in this position of this liquid dropping out. This is multi-phase flow. So there's other terms you hear on this as well. There's the Cry-Condon bar and the Cry-Condon therm. The Cry-Condon bar is a line across here. Basically, it's the pressure above which multi-phase flow won't exist, and the Cry-Condon therm is the temperature above which multi-phase flow won't exist. So this can be bounded by these two lines, basically, cricondom therm, cricondom bar. So now above this area, if you think about pipeline operation, this is a pipeline MSC. Above this, we've got a region which we call dense phase. If you were to operate at a relatively high pressure, you'll see that irrespective of what temperature you are, you don't get liquid dropout. It's just you get one continuous phase. So what you get is a change in density and viscosity between here and here, but no liquid forming. So one way of transporting a product which would normally be multi-phase flow is to increase the pressure, and we call this dense phase operation. So particularly for and there are a number of pipelines around the world that operate like this. The disadvantage is you have a very thick wall because you're operating at something like 170 bar, 200 bar up here. But the thing is, you're in ambient at you've got no liquids basically. And LPG is pressurized gas at low temperature. That's down. LPG is down here somewhere. The LPG is, I think, is in two phases in the tank. Actually, it's down here somewhere. It's an ambient temperature, but at a relatively small pressure. And LNG, very very low temperature but liquid. So it's way down here sort of thing. But at ambient pressure. So, any questions on that one? That's an important aspect of multi-phase flow, because you're when you do a multi-phase flow analysis, one of the important property predictions is figuring out where you are in here.
The black oil refers to the impure oil, dirty oil?
Not exactly. I think it's a term that it's a way of differentiating between different product types, basically. So you can say, a gas condensate. It's light colour, virtually transparent, maybe a greeny sort of colour. Well, this is black. It's opaque. That's literally. So it's a definition of. But it's not black because it's got contaminants, and it's black because it's got these heavier rains that make it that black colour, basically. So it doesn't refer to contamination. So in terms of reservoir properties, these are typical reservoir properties. You can typically think about defining reservoirs in terms of the fluid type. We've got the terms volatile oil, black oil. The initial gas-oil ratio. So this is in what they call in standard conditions. So if you take the oil in the reservoir, take it to 1 atmosphere and 20 degrees centigrade, for example, then it's what do you have? So for a volatile oil reservoir, you get particularly between 2,000 and 3,500 standard cubic feet of gas per stock tank barrel, basically. So that's and then there's this term API gravity. API gravity is actually, you can relate directly to density, basically. So it's an API gravity which is greater than 40. So the higher the API gravity, the lighter the density, basically. The less the heavier hydrocarbons, basically. Colour of the liquid, stock tank liquid, black, orange or green. Light, relatively inviscous, I would say. So stock tank liquid formed in the reservoir, and then black oil itself, not much gas, less than 2,000 standard cubic feet per stock tank barrel, less than 40 API. less than 40 API, black or greenish colour, stock tank liquid formed in the reservoir again. So So fluid types, dry gas, that's incredibly unusual actually. Very rarely come across completely dry gas in a reservoir. So just gas, no water, and no other hydrocarbons it does happen, but it's very, very unusual to get that situation. So no liquid, no stock tank liquid, no stock tank liquid, no stock tank liquid, basically just dry gas. Wet gas. Wet gas is it basically takes 50,000 standard cubic feet of gas to get one stock tank barrel. So wet gas. Wet gas is obviously two-phase flow. And when we talk about wet, we're not just talking about water. We're talking about hydrocarbons. So it's hydrocarbon liquids and water liquids. Water, white, transparent, between 40 and 60 degree API, the liquid. And then gas condensate. Obviously less gas, but still some gas. So 3,300 standard cubic feet per stock tank barrel. 40 to 60 degree API, light coloured brown, orange, green, water white, again, gas condensate. So you can get a huge variety of different types of hydrocarbon reservoirs. So from dry gas to thick viscous crude. You know, some crude, API crude, it's possible to get API crudes of like 9 and 4 and 5 API, like tar. Someone like Venezuela produces those very, very thick crudes. I think there's some in Kuwait, these heavy oil fields in Kuwait as well. So some basic processing. So we've got it out of the reservoir. The thing is, what do we connect our reservoir to? And this is pretty much how oil treatment works. These are our wells. We've got a production well basically. We talked about test separator. So you'd either reduce to the test separator or the production separator. Also in the well you'd have things like chemical injection. Chemical injection could be for wax inhibition. It could be for hydrate suppression. So effectively it's the chemicals you need to produce your liquid. Hydraulic package is to control the well, to operate the valves, operate the choke, measure temperature. Okay. Oh, sorry. Is it because I'm in the way? Yeah. Sorry about that. I can stand on the other side, but I'm right-handed. A little.
Start to move again.
Yeah. I should leave him around a bit more. So production separator and then the oil treatment separator. Production separator, and then you effectively the production separator. You're splitting the product into three different things. Gas coming out the top to the gas treatment, and then you've got oil to oil treatment, and then you've got water treatment. Now water, you've got no use of the water. It's possible you could re-inject it, but normally you dump it to the sea. So there's a whole kind of water treatment thing which is tidying it up, getting rid of. There's a number of different processes to get rid of all the oil, get rid of all the gas, basically, so you can get rid of it, effectively get rid of the water. Obviously, the gas and the oil are valuable products, so they'll be treated in some way. I think the next few slides will deal with that. And then into your pipeline, and you have pig launchers basically to clean the pipeline. So that's a very basic oil treatment schematic. Often you have a number of different separators. There's a high pressure separator, medium pressure separator, low pressure separator. So again, this is our production well. This is a subsea flow line, and these are all control valves. And these are level controllers. So the way a separator works is it has a level controller on the water. When the water goes up to a certain level, it trips the switch, opens up the valve, and then reduces the water. That will close, so you can control the level of the water in the separator. And the same with the oil as well. You have a level controller, a control valve basically. The temperature at which you separate oil can be quite critical. if the temperature's too low, it won't separate properly, basically. So you'll get water, oil held up in your water, and you find that you'll be losing product and also hard to clean the water up. So sometimes if you actually have to heat up the oil before you can separate it. On the other hand, if it's too hot, you have other problems. So hence the term heater stroke cooler, basically. So these are reducing pressure, high pressure, medium pressure, low pressure, and the gas goes off to your gas processing, or in some cases it'll be a flare. Less so these days, but certainly used to be the case. The gas was disposed of, and when I worked offshore, it was disposed of. So, but now they tend to collect it and compress it and use it, try and use it as a product. And eventually you get, the eventual product is what they call dead oil. In other words, dead oil is it doesn't have any gas in it. So it's effectively has a very low vapor pressure or an atmospheric pressure. No, there's no gas in it. Effectively, dead oil is the term. So, and if it's still hot, you cool it down and then you pump it to your export, to your ship or your pipeline or whatever, basically. So very simple process, really. Hydrocarbon processing, upstream hydrocarbon processing is incredibly simple compared with downstream petroleum products. You know, catalytic processes, cracking. You know, that's quite complex. I would say orders of magnitude more complex than hydrocarbon upstream processing. It's incredibly simple. So, because it's on and offshore platforms, it has to be simple. So, and this is kind of the building block of oil processing, the separator. This is the conventional kind of gravity-based thing. Spooky wind. So the inlet, you've got a momentum absorber. So you get, if you're going, this is multi-phase flow. If you're getting slugs of liquid arising, it's taking out the momentum. So you're not creating waves. You're not creating waves here. You want it to be relatively flat. And then you've got here a weir. So it's falling. The water product's falling down into here. The oil and water are separating by gravity. So you can drain the water out here based on a level controller. You can drain the oil out there based on a level controller. Obviously, then the gas is coming in here. Obviously, you don't want droplets. There's a chance you're going to get droplets of oil in the gas here. So you've got a mist extractor. So you don't get gas. Imagine that, there's a feral velocity going up there. You don't want the gas to go whizzing up there into your gas treatment. So that's a fundamental building block of oil treatment, basically. So you might have 1, 2, 3 of these in a row, basically, to get it down to export quality. Any questions? The other way you can separate oil is to use what they call a hydrocyclone. I don't know if you can see this, but it's it basically uses the centrifugal force. So the oil and water mixture goes in there, and it spins around due to the geometry and the velocity. It's quite a high velocity, and as it spins round, the less dense ones are flung to the outside, basically. Actually, no, the more dense ones are flung to the outside. So the water is as it spins around, the water is flung to the outside of that vortex, and the oil ends up being in the middle. So the oil goes out the middle, and the water goes out the bottom, basically. So a hydrocyclone. I think there's a Kirby vacuum cleaner that uses this technique as well for separating dust from air. So hydrocyclone. In fact, you get hydrocyclone filters for gas as well, using the same technique. Centrifugal force, basically. So one problem with this technique, of course, is that you need a high flow rate here. So the question is, how do you deal with variable flow rates? Because not all, not in all situations can you rely on a continuous flow. You might have to change for some reason. You've got workovers on wells. So the way it works is that you have a number of these in a bank, and you switch them in and out depending on the flow rate. So you can have, if you want to reduce the flow rate, you just use less of them basically. That's how you actually maintain your flow. So maintain the efficiency of these. So gas treatment. So that's oil treatment, gas treatment. So why do we need gas treatment? We need it to reduce water content, to prevent water condensate and hydrate formation, to lower the hydrocarbon dew points, to prevent condensate of heavy hydrocarbons. So we're taking out oil, we're taking out water, and to prevent hydrate formation. Potentially by the injection of hydrate temperature depressants such as glycols and methanols. And the gas may be required. You may be required to increase the gas pressure to export it for a sales pipeline, to use it as a product, or to use it as gas lift to increase the productivity of your oil in your gas lift reservoir, in your gas lift system, or dehydrate it, or for dehydration and dew point control, or for re-injection into the reservoir. The reason why you might inject gas into a reservoir is because if you put gas back into solution, you actually change the properties of the oil. So you can actually use it as a production enhancement technique. So, and also you can't we've got since the Kyoto Agreement, most nations have signed up to flaring less gas. Because flaring gas, obviously, you're producing greenhouse gases. And obviously it's a waste of energy. So, if you can re-inject it into the reservoir, you can kind of avoid the flaring issue. So, some people will call it an underground flare. So it's not necessarily completely a legitimate use of gas, but it's less obvious than flaring it. So. And gas dehydration. This is a bit busy, but this connects basically to the other chart I showed you. This is the connection from the low pressure separator, medium pressure separation, and the high pressure separator. But it's kind of the other way around. You're starting with a high pressure and going to a low pressure. So if you can imagine that from a process point of view. So you get the gas from the low pressure separator. You may cool it. And then it goes to a knockout drum. So if you get any further liquids that dropped out of the gas, basically you can put those back. You can knock those out, and then you compress the gas basically. Is that me? You can compress the gas, and then cool it. And then you're back into the you knock any further liquids out, compress it again, cool it. It's hot when it comes out of the compressor, etc., etc. And then this is the connection for the high pressure. Now it's at a high pressure basically. And then you can effectively export it. Knock out any water, stabilize it, compress it, cool it, and then meter it, and then send it for export. So the gas dehydration is an important thing. So this is effectively this is a glycol plant, and it's used for separating water or taking water out of gas. So it works. You get moist natural gas coming in. You knock out your hydrocarbons and send them back to a liquids tank, and then you effectively sprinkle down glycol over the gas effectively. So the gas is moving is going through here. Comes out the top, and then you get effectively dry natural gas, and then the glycol is separated, boiled, and then recircled. So you've got two fluids. You've got fluid circulation basically. So you've got rich glycol, rich in water coming out the bottom. You remove the water and then put it back in again basically. So it circulates basically. So it's the way of removing removing water from your gas. And H2S, various ways. One way is to use a chemical scavenging thing. Sulfurite. This is one is a trade name. So you've got inlet sour gas. You put it through the chemical basically, and you get sweet gas coming out. And there'll be a way of either replacing the chemical or cleaning the chemical using another process basically. So. And there's a similar way of removing CO2. Same thing. You've got a CO2 absorber, H2S or CO2 absorber, basically. Using a solvent. Amine is one of the ones the solvents they use. So you got feed gas coming in basically, and they use the absorber basically, and you circulate the solvent and clean it up basically. So. Any questions? So what the time is? 10:30. So I think we'll have a break when we get to the end of this section. Is probably the best thing, isn't it? So there's two sections. I think we're about 75% through the first one. So yeah. So where processing. This is the location of processing equipment. Very much down much down to economics. If you produce product from a reservoir, if you can avoid a platform completely and just go all the way from your subsea development all the way to the shore, then that's perfectly feasible. But generally speaking, you can't do that because you need to treat the gas. You'll get hydrates. There isn't enough pressure driving force to get it to go all the way to the beach. Get it all the way to the shore. So typically you're forced to put platforms offshore, and therefore you end up with processing on a platform. Now you might want to minimise it here, so you do the absolute minimum here, enough to allow you to produce to the shore, and then when you get to the shore, you do the rest of it basically. So you may not knock out everything, but just get it into a point where you can relatively cost effectively produce it. So because it's so much cheaper doing stuff onshore than it is offshore. Because for every ton here, you've got hundreds of tons of jacket underneath it, to hold it up basically. And you've got people having to go back and forth with helicopters. You've got to maintain it. It's in the middle of the sea. You want to avoid as much as you can out there. So jackets are typically, but there are some deep water jackets, but typically associated with relatively shallow water. 160 meters is, I would say, is jacket, certainly jacket territory. There have been 300 meter jackets before, 300 meter, but they're some of the largest in the world. But the more common technology now is to actually put it on something that floats, like an FPSO, floating production, storage and offloading, with a tanker. So here, unlike with the jacket, you've got the production well going right up with a Christmas tree on the jacket in the dry. You've got a wet tree basically. With the jacket, you've got a dry tree. Here, you've got a wet tree. The actual Christmas tree and the wellhead are actually on the seabed, and you're connecting to a manifold. And then the manifold's connected to a riser, and then the riser's connected to the FPSO basically. So a lot more complicated. And you've got all this stuff to maintain as well. It's now it's in the wet. You need divers, you need dive support vessels or ROVs to operate and maintain this. These are wells, 12-inch production wells, gas lift, distribution. And here you've got a number of risers, because you've got probably production riser, test riser, water injection riser, gas lift riser, umbilical for control, so all going up to the FPSO. And then you've got an export riser, along a subsea pipeline to an SPM, and then the export tanker basically. So you're putting your production equipment here on something that floats. And if you think about the production the separator I showed you that works on gravity, if you imagine that in a moving environment, so designing equipment that can be used, that needs to be is light enough to put onto a floating facility. You know, big high towers, for example, don't work very well. You know, something that relies on gravity, obviously you've got potentially got movement to worry about. So hydrocyclone is lighter, maybe that's a more applicable technology for an FPSO, hydrocyclone. So. An important thing about an FPSO is the turret. So it's not particularly an issue for multi-phase flow, but basically you get the point that's fixed with anchor chains on it, and all the risers connecting to it, and the FPSO moves around it, and then you connect the process equipment on the FPSO to the risers through what they call a swivel. So you may have about 10 different swivel connections, basically. So the FPSO can rotate indefinitely around the turret, which is fixed in space with its anchors and its risers, basically. So you can see here. Here's the anchor chains. This is the turret configuration, bearings, and then this is the production swivel, basically. But you may have multiple. So this is an incredibly expensive and very elaborate piece of equipment, so it can go wrong. So I know Tullow Oil mobilised their 10 FPSO to West Africa, Ghana. Installed the whole thing, got it operating, and then realised they had a problem with their turret, and then had to disconnect everything and take it back to the dry dock to fix it. Incredibly expensive. So I can imagine someone had a few sleepless nights over that one. So we've got production platforms, productions, FPSOs. The other very specialist sort of production is seabed production, subsea production. Very, very rarely done. Very rarely done. It is done occasionally, but it's very rarely done, basically, because there are so many complexities to dealing with it. Basically, everything subsea. Imagine all those control systems, those level switches. You know, all those different processes. Imagine doing all that subsea, basically. The reliability, and making it reliable. But there are, you know, this company Alpha Prime. I'm not sure who owns it, what happened to it, who owns it now. But you know, specialised in subsea production equipment, basically. So. Where it does come into its own subsea production is where you have if you had a big platform which is fully to capacity, it could take oil, but it can't do any more processing because it doesn't have the capacity for water or gas, or so you can produce oil to it. It can't clean up your oil because there's not enough space on top sides to add the extra equipment. That's where subsea processing might come into its own, because you can process it here and then just send the oil to the platform. But you imagine producing water to sufficient quality to be able to dump it into the sea, subsea, is quite a challenge, basically, to maintain and keep all that equipment working. So any questions? Any questions about that? So on single phase flow, I'll talk about this first because I know this is on multi-phase flow, but the principles are extended from single phase flow. Really, it's you've got to really understand single phase flow to understand multi-phase flow. So it's the basic flow equations. Piece of pipe, L or DL. Pressure in, pressure out, height dz. It's got 3 bits. Oh, I've lost my heading there. 3 bits. There's the considering really pressure drop here, really on a piece of pipe. So the pressure drop, it's got 3 components: the frictional components, an elevation component and an acceleration components. The frictional component is has a thing called a friction factor in it, F. So it's a friction factor by the density multiplied by the velocity of the product of the fluid squared divided by twice the diameter multiplied by the length. That's known as the Darcy-Weisbach equation. Very, I'm sure it'll be familiar to some of you. It's a classic piece of you can derive it from the steady flow energy equation. And then you've got the elevation term, gravity by density by the difference in height. Very, very simple. The thing about this one is that for single phase flow you get it back again. So if you go up a hill, pressure reduces when you get to the top. When you come back down the other side, you get it back again. With single phase flow you don't get that. Sorry, with multi-phase flow you don't get that. Multi-phase flow is not reversible. You lose energy going up, you don't get it back again, basically. So reversible with single phase flow. So when you consider a single phase flow, you can actually consider, irrespective of the variations, you only need to consider the difference between the inlet and the outlet for single phase flow. Even if it's gone up and down mountains, whatever, it's only the difference between the inlet and outlet that actually matter. Because you get it, whatever you do, you get it up, you lose it, you get it back, you lose it, you get it back. The difference is important. So. And this is the acceleration term, difference between velocity squared, so the energy used in accelerating the product. So, which is normally pretty well, for steady state conditions is nothing. So. And you add all that up to get your total pressure drop, basically. So I think we're going to talk about friction factor now. So the friction factor, that's the term. Oops. Friction factor, basically our pressure drop is proportional to the friction factor. And the friction factor is a function of the Reynolds number, the roughness and the diameter. And the Reynolds number is a dimensionless group, which is typically a very high number for a fluid in a pipeline. So it's a relationship. The mu, that's not very good, is it? So it's a relationship between the density and the kinematic viscosity, basically. So Reynolds number, if it's less than 2,000, we call that laminar flow. Greater than 2,000, turbulent flow. So laminar flow is literally laminations, laminar. So it's all moving together along the pipeline, like in stripes. Turbulent is as it describes. It's a complete mess. Each particle trace will be almost random. Turbulent flow is actually more efficient. Laminar is actually a very efficient way of flowing. Now, if you want to work out the friction factor for laminar flow, it's incredibly straightforward. It's basically 64 divided by the Reynolds number will give you the friction factor. So for Reynolds number greater than 2,000, there are a number of different equations. I would say the most accurate equation is it's called Colbrellt-White. The Colbrellt-White equation. And you can see this is the friction factor F, and it's on both sides of the equation. So if you want to solve this in a spreadsheet, which I was doing yesterday, coincidentally, then you have to do it. Iteratively, using an iterative technique. But it's fairly easy to do that. So, but there are a number of approximations for the friction factor for turbulent flows which you could use. So the Colbrellt-White equation is used to derive what we call the Moody chart. It's probably this is probably too small to see, but this is roughness. Actually, it's relative roughness, which is the roughness in millimeters divided by the diameter up here, and then this is the friction factor here, and this is the Reynolds number. This is the Reynolds number along here. So the idea is you work out your Reynolds number, work out your relative roughness, and where they cross, gives you your friction factor basically. So it's a lookup chart that if you know your roughness, you know your diameter, gives you relative roughness, and you know your Reynolds number, you can get your friction factor basically. So these are low Reynolds numbers down here. So you remember for low Reynolds numbers, it's 64 divided by the Reynolds number is the roughness. So that's what that line is. So that's the 64 divided by the Reynolds number is the line for the line for laminar flow basically. And for very high, you can see for very high Reynolds numbers, it ceases to become a function of Reynolds number, the friction factor. So this is called laminar, this is called transitional, and this is called completely turbulent flow basically up here. So. Any questions on that one? I don't know if you can see it, but I think you get the general principle. So, yeah. So roughness, probably worth saying a little bit about roughness. First of all, it's not actually a physical measurement. So you don't take a piece of pipe and get a ruler out and measure it and say this has a certain roughness, because it's more complicated than that basically. It's normally worked out experimentally. So you'd actually measure the pressure drop across a piece of pipe and work back to the roughness that gives you that pressure drop based on the Darcy equation. Or the Colbert-White equation and the Darcy equation. So typically a roughness for a conservative steel is 0.05 millimeters. Clean steel 0.02. Heavily corroded steel can be as high as 1. This is what's published, but I know from my own experience, if you measure the pressure drop for a very heavily corroded light water injection line, for example, and you work back to the friction factor to give you that pressure drop, I've actually worked out under some situations you'll get a roughness of about 5 millimeters. So you can. So I think the lesson from that would be that when you start off, you might have 0.05 millimeters. But the trouble is, when it becomes corroded, it might end up being 1, or might end up even being 5. So the danger is, you need to really consider the corroded condition when you're considering your hydraulics of your pipeline, basically, particularly if it's very sensitive to roughness. So to consider clean steel is fair enough, but it's not going to stay clean steel for very long. So. Also, it is affected by other things like wax, for example. You imagine wax deposition will actually reduce roughness, which is a good thing. So, for flexible pipe, rough bore flexible pipe has a significantly higher roughness than steel pipe. You can actually calculate by dividing by the diameter by 250. So if your diameter is 250 millimeters, then your roughness will be 1 millimeter. Strangely enough. So moving on to multi-phase flow now. So that's sort of single phase flow. We talked about the Darcy equation, talked about Colbert-White, talked about roughness, talked about friction factor, Moody diagram. Just to recap, really, phase envelope, we're talking about in here, basically, multi-phase flow. Just a quick word about dense phase. Dense phase, as you'll probably remember, is up here. Such a significant pressure, such to a point where temperature won't affect the, you won't get any liquid dropout, basically. So advantages: high capacity, is very efficient. Low delta pressure. If you compare it with multi-phase flow, you've got a relatively low pressure drop. Avoids uncertainties. Multi-phase flow, you've got lots of uncertainties. You've got wax, hydrates. You've got liquids being produced. You've got the uncertainty of the calculation. You've got all these complex multi-phase flow equations to worry about. So it avoids all of that stuff. So something which you need with multi-phase flow typically is a slug catcher, because you're getting gas and liquid being produced at the end of your pipeline. The question is, what do you do with them? So typically you have a big vessel which catches the liquid. So the gas goes off, the vessel's caught in the big liquid, which is then produced at a slower rate. So, and slug catchers, because they're operating at pipeline pressure, you need very, very thick steel. They end up being very, very expensive bits of equipment. So they're very expensive. So again, dense phase avoids the use of a slug catcher. Disadvantages: you have to have gas compression. If you talk about an offshore platform, you've got big, expensive compressors on an offshore platform, so there's costs. You're going to have to take out, completely remove the water, because obviously water and high pressure would form hydrates, so you need to completely hydrate your fluid, dehydrate your fluid. And also, if you think about a dense phase line, how do you actually start it, get it, shut it down and start it up? Because your gas is, your product may be multi-phase flow on your top side, so how do you actually start up your line? Do you pressurize it with nitrogen and then slowly introduce your product? And then if you need to work on it, you need to work on that line. If you reduce the pressure, obviously you're getting liquids forming. So how do you maintain that line if you need to repair it? If it's hit by an anchor and you need to cut a section out and repair it, how do you actually do that when you're going to get this second phase coming out? Greater pipeline wall thickness, high pressure, so you're getting a lot of extra material costs. And as I said, it's quite hard to depressurize it really. So if you can see that, these are different ways of producing a pipeline or a reservoir contents using the pipeline. You can export the whole stream as multi-phase or dense phase, or single phases split into gas and liquid. Basically. So these are the different three principal ways of exporting multi-phase products: separate, multi-phase flow, or dense phase. So. Any questions? Clear? So multi-phase flow terms, it's quite full of jargon. Multi-phase flow. There's a thing called the flow regime. Because you imagine water, you imagine multi-phase products in the line. There's different ways in which they can be transported down the line, and I'll show you those in a minute. But so the flow regime is the name given to the way in which the two phases are being transported in the pipeline at the same time. So. Liquid volume fraction. At any temperature and pressure for a hydrocarbon product, you can actually work out how much gas and how much liquid is present, and that's known as the volume fraction, which is those lines on the hydrocarbon phase envelope. That's effectively the volume fraction. So. And liquid holdup. If you think about a pipeline, you've got when you're producing multi-phase flow, you can actually work out how much liquid is held up in that pipeline. So you've got gas and liquid at the same time. The hold-up is that total liquid, and also there's the individual hold-up. So you can consider it section by section, because it will vary along the line, or the total hold-up. The reason why that total hold-up may be of interest to you is because, generally speaking, the efficiency of multi-phase flow goes down as hold-up increases. And if you run a pig through the line for any reason, you'll find that total hold-up will actually be produced to your process or to your slug catcher or your process equipment. So that's total hold-up. We talked about the different mechanisms in which fluid travels down the line. Well, one mechanism is slug flow. So it's like a chunk of liquid travelling down the line on its own is a slug. And when it gets to the end, you need something to catch it, so you have a slug catcher. Within analysis, again, there are other terms that come into play. There's there's a term which is only really used in analysis of multi-phase flow, and they call it superficial velocity. And it has a rather superficial definition as well. It's the velocity that the liquid the fluid would have if it occupied the pipeline on its own. So if you have a very small amount of oil being transported down the pipeline, then that would have a very low superficial velocity. And if it's the majority of its gas, then the gas velocity will be similar to the superficial velocity. So, and if you add the superficial gas and superficial liquid velocities together, you get the mixture velocity. Now, a flow map is a device that determines what flow regime you have. So literally, it's a map, and it's normally got a couple of different correlated parameters, which tells you, and then you can figure out on that map where your flow regime is. So within a multi-phase flow calculation, there is a definition of the flow regime using a flow map. And then there's two correlations that work hand in hand. There's a pressure drop correlation. So that's a little bit like, you could say, the Darcy-Weisbach, the equivalent of the Darcy-Weisbach, but for multi-phase flow, the pressure drop correlation, and then also the hold-up correlation. Because pressure drop is a strong function of hold-up, you need a hold-up correlation as well. So we predict the hold-up, predict the pressure drop, and then the other very important thing, of course, is the fluid property predictions. So at any point in the line, we need to know what our fluid properties are. We need to know how much gas is present, how much liquid is present, what the viscosity of the gas is, what the density of the gas is, what the viscosity of the oil is, what the viscosity of what the density of the oil is. So we use these property predictions. So you come across all these terms when people talk about multi-phase flow, or you read about multi-phase flow. So hold up has various correlations. What this chart is demonstrating is a very strong function of slope. This is the angle of the pipe from the horizontal to the vertical, minus 90, plus 90, and this is the liquid hold up fraction. So liquid hold up can be expressed in terms of barrels, in other words, a total value, or just a fraction. So at any particular point of the pipeline, so the little bit of pipeline that we're referring to, which has this slope, 0 will be no liquid, 0.5 will be half of the pipeline as liquid, basically. So you can see when it's sloped down and up, the hold up changes quite considerably. So basically, it's hard to get liquid to run up a hill. You know, if you're trying to get liquid to run up a hill, you need the gas to be whizzing past it to force it up through friction. But it's very easy to get it run down a hill, so hold up will increase when you're going down, basically. So, and in generally speaking, multi-phase flow is very sensitive to slopes. So when you model it, you need to model all the ups and downs, rises. Slope is incredibly important for multi-phase flow. Has a very, very strong function of slope. So. How are we doing for time? 11 o'clock. So. You must be getting tired. Not too much more for this start. Yeah. Okay. Generally, you can generally think about multi-phase flow as like horizontal regimes and vertical regimes. And these are the horizontal ones. And they're split into three groups: segregated, intermittent, and distributed, basically. So segregated is like horizontal stripes, if you like. Stripes going that way along your pipeline. So the first one there is stratified. So it's literally a strata of liquid, like a strata of rock. High gravity, gas on the top, liquid on the bottom. And as you increase the velocity of the water of the gas, you get wavy. So you get literally waves forming on top of the liquid as the gas whizzes past it. So, and then annular. That's the liquid travelling up the outside, travelling along the outside with the gas whistling down the middle. So they're the stratified flows. Intermittent. Now we're talking about stripes in the vertical sense. So segregated, separate by gravity, and then intermittent slugs moving along the line. So slugs and plugs. And then distributed, or the other term for that is homogeneous. So here there's not much difference between each part of the pipe. So we've got mist, small amount of liquid, large amount of gas, typically flowing at high velocities like an aerosol almost. And bubbles the other way around. Basically, you've got small amounts of gas in liquid. So bubbles going to the top. And it's quite possible that you can go from one to the other. In fact, if you play around with it, you can actually get in a situation where the fluid comes out of the reservoir, gas comes out of solution, and you get segregated flow, stratified. Pressure reduces, you get further gas coming out, and it becomes wavy. So the gas whizzes across the top, and you get waves forming. You find these waves reach the top, and then they become slugs. So you get slugs moving down the pipeline. So you go further down the pipeline, and then the gas continues to come out of solution, and you end up with mist. So it's possible you start with stratified, move to wavy, move to slug, and then move to mist in one pipeline. So the efficiency and pressure drop and implications along that pipeline are quite profound. So these are examples of vertical flow. Bubbles, a bit like a pint of Guinness. The bubbles going up, being transported with your product. Imagine in a well, you're just producing from a reservoir. You've just gone below the bubble point. You're getting bubbles just starting to form in the matrix of oil. You get this type of flow. Basically, it's two-phase flow. It's relatively efficient. Slug flow, you get plugs of liquid going up. And churn is interesting because imagine in a vertical flow you've got some instability, so you can get flow of oil up being driven by the gas moving past it, and then it can become unstable and then fall back down again. So you get this circular effect. And annular flow, you get the gas whistling up the middle, basically. So with just the liquid on the outside. So a special example. So we've got horizontal flow, vertical flow, but actually when you do multi-phase flow analysis, you'll find that some correlations will actually have angle in them. You'll find some correlations, hold up and pressure drop correlations, are for either for that or for that. But some actually have angle built into them. So you might find with some correlations you have to have a switch. So you can say anything more than 45 degrees, I use vertical. Anything less than 45 degrees, I assume it's horizontal. Where some correlations actually have the angle in them. So that's again part of the analysis. So. And this is a special case. This is where you actually intentionally make two-phase flow to help you. And this is a gas lift well. So this is the annulus. This is the production tubing. These are gas lift side pocket mandrels here. This is a sealing collar. That's not the right term. I can't remember what it's called. So the idea is that this is the reservoir down here. These are the perforations. So you introduce gas into the annulus, and then you have these side pocket valves which let gas go through at a certain pressure, basically, and that aerates. It doesn't aerate because it's gas. That produces multi-phase flow by the introduction of gas, which reduces the density, which increases the flow rate. So it allows your production of your well to increase. So the gas reduces the well-specific gravity, decreases the static head, allows the flow rate. If you keep increasing that gas, though, you'll find eventually, because the velocity in here is increasing, it will choke. So there's like an optimum value. If you start increasing that gas, the flow rate will improve, and then it will start to get worse. The other type of two-phase flows worth talking about is the terrain effect with pipelines. If your oil is not completely dead, it's still got some gas dissolved in it, and it will have a vapor pressure which is above ambient. You'll find that this is a pipeline. This is basically height in meters. This is distance. So this is effectively a pipeline going over a mountain. That's height in meters, and this is pressure in psi. So this is the pressure. This is the pressure inside of the pipeline, basically. But you can see as it goes up the mountain, you can find that it goes below the vapor pressure. So you get what they call a vapor lock. So you get gas coming out of solution and actually causing multi-phase flow and reducing efficiency. So that's actually a bad thing for a pipeline. You'll reduce the transportation efficiency of the pipeline. So. These are some little slides, I hope they work, of a multi-phase flow regime in pipelines. So they're a little bit temperamental. So let's see, let's hope, fingers crossed. I think it's working so slowly though, is the trouble is the modern versions of Office don't allow you to run applications and things. We're a bit fussy about it. Ah. Oh. It's not actually moving on the screen though, is it? Great. Fantastic. I think we're gonna. I'll describe them, okay? Yeah. Yeah. Basically, there's a transparent post-back tube rig in Austin University of Texas in Austin, and they're videos basically of the different flow regimes. So in this one, it's in the larger pipe, and you just see pretty much a very, very unimpressive just interface of liquid which is segregated flow really. So things are happening very slowly, very straightforward. And then this one, the larger diameter transparent pipe, you just see waves, gentle waves on it as it's going through. And then on this one, it's like slug flow. It's actually in the smaller pipe, in the return pipe, and you see this fluid whizzing backwards and forwards, whizzing very, very fast through with all sorts of troughs. So.
Could you please upload these videos to Factor so we can see it?
Yeah, sure, yeah. I think the problem is the new version of Office is very fussy about running security and things. You know, it's hard to get it to work. So it's not very unreliable. But yes, I will. Yeah. And froth. Froth is, there's a lot of, actually quite a bit of violence. You know, as the thing improves apart. The difference between the slug flow and the segregated flow is absolutely enormous. You know, you can see the whole rig almost moving with the slug flow. And you've got this whizzing past basically, with all sorts of froth. So quite violent, completely different. So this is very sedate and boring, and this is really going for it. So I'm going to try pushing another one and see what happens. Pathetic. Sorry about that. Yeah, I recently upgraded to Office 365. I think that's causing the problem. So it used to work. Slugs of liquids in this image pushing pockets of gas through, and this is in a completely vertical sense. And you can see this looks exactly like a pint of beer that you poured very quickly, like fizzy lager. And you can see the bubbles sort of rising up. Okay. Yes. Yeah, you see the slugs of liquid pushing gas through the inclined pipeline. So it's quite violent, really, in comparison. Go on. So inconsistent as well. And transitional is like a transitional between slug and bubble flow, basically. So you've got it literally flips back between the two. And this one is churn flow, and you can actually see the liquid sort of falling back down again, basically. So it's not consistently going up. It's churning, as I say, churning round and round, basically. Oh gosh. Okay. So that's the bubble flow. Should we try the churn one? I think you just have to wait. Maybe that's the secret to it. I wonder what it's doing. Ridiculous. Yeah. Ah. So this is the churn flow. So unstable basically, not very efficient. Bits of it's got falling back and then being picked up again, and then literally going around in circles. So these are examples of flow maps. I'm not really trying to go into a huge amount of detail here, but what I wanted to demonstrate really is that these are different flow maps: uphill flow, horizontal flow, downhill flow. So you can see the stratified flow, the very sedate one I was showing you about, produced by gravity, will exist downhill, will exist horizontal, but doesn't really exist uphill. So you can't get it. You can't get it up. Get it to go uphill effectively. So these are examples of vertical flow map. These have different. They're very much different parameters. You'll find for different researchers. There's a lot of different schools of thought with multi-phase flow. Lots of different researchers. They're normally named after people. This has got bubble flow, froth flow, plug flow, slug flow, mist flow. For small amounts of gas, for large amounts of gas, small amount of liquid, basically. So the main parameters here are volume factor and flow rate. So if you get a small amount of gas, small amount of liquid, high velocity, you'll get mist flow. Large amount of liquid, small velocity, you get segregated flow. That's generally, and then between, you get the slug type flows depending on orientation. So orientation, amount of liquid, and flow rate. They're the main factors. So, and again, loads of different sorts, different examples of horizontal flow maps. You see stratified appears here. So to do any kind of analysis, you need some way of predicting properties. So generally speaking, this will be included in the multi-phase flow program. So it's knowing what properties are at any one time. And there's two sorts of ways of predicting properties. One is using a correlation or black oil model, which is where they've actually made physical measurements and then come up with a formula or a curve fit that actually replicates the properties of the measured product. And typically these are used for black oils, which is the description of the product. Now for gas condensates, there are no black oil models, so you have to use a compositional model. And the other term for a compositional model is an equation of state. So you plug in all the different compositions, and there are tables of coefficients within the calculation method. And these are various researchers that have come up with what we call equations of the state. They predict fluid properties from the composition at temperatures and pressures. And these are the three main ones: Peng-Robinson, Benedict Webb-Rubin, and Swerve-Regelich-Kwong. This one was written in the 1930s, so they go back quite some time. And I wrote a program to do one of these once, a long time ago. These are typical black oil models. Phase equilibria. That's how much is present of gas and liquid at any one time. Phase equilibria. So Lassiter, Standing, and Glasso phase equilibria equations. Oil density, Vasquez. Gas density, Standing Katz, Weichert as is. Oil viscosity, Beggs-Robinson, Beal. Beggs-Robinson for dead oil. Beal's based on a logarithm with two different temperatures, two different pressures. And then gas viscosity, Lee, surface tension, and Baker, Swirlroth, basically. That should be highlighted. So for single phase flow, I'd certainly recommend single phase flow is also the Moody chart, which I've shown you. Whether it's for gas or liquid, equally valid. But there are a whole bunch of these equations that you'll see referenced, particularly from American publications. Panhandle A, Panhandle B. Panhandle refers to part of Texas. These are, I would say, pretty old-fashioned now. Actually, I mean they're not typically used. pretty much all hydraulic analysis I've ever done has been based on some kind of program, or Dicey, Weisbach, Goldberg, White, not using these correlations. So, and again, it's not something you need to memorize, but I think the important thing you need to know is that with multi-phase flow correlations, there are lots of different correlations for different sets of circumstances. Very famous one is Beggs and Brill. They're some of the very earliest researchers into multi-phase flow at Tulsa University. And there are some of the early research was done with water and carbon dioxide by Beggs and Brill in little 2-inch pipes. They did their research. But more recently in Norway, they produced massive, great big flow loops. And there was one of these in Bedfordshire as well, Cranfield, where you can actually come up with, you can actually compare what happens in reality with real oil and gas with the correlations. So these are examples of real flow loops. So. And there's applicability as well for various flow correlations. Different. This is actual single phase. We see Moody applicable for everything. That's the chart, so you may as well use that. It's easy. So, and then you don't need to remember this. The principle is you've got different circumstances, and there's different researchers' work is applicable to different circumstances. So you've got vertical and predominantly vertical oil wells, so down, up, highly deviated horizontal wells, vertical gas condensate wells, oil pipelines, gas condensate pipelines. So you can see some are not applicable, some are applicable. So when you're doing a multi-phase flow analysis, you have a range of applicability for your particular set of circumstances, and you'll switch from one to the other. So when you go from your deviated well to your vertical well to your pipeline to your riser, you'll switch between the various flow correlations because of their various applicabilities. So you should have this on your blackboard. So, hope so anyway. So what's recommended? Single phase systems, Moody. Vertical oil wells, Hagedorn and Brown, highly deviated, Duns and Rowe, all gas. All gas is based on some Norwegian research, and out of that Norwegian research, they came up with a program called Olga, which is a transient dynamic multi-phase flow simulator, which is very expensive. Gas condensate systems, Hagedorn and Brown, oil pipelines, Oilemans, and then gas condensate pipelines, BJA correlation, Baker Jardine Associates correlation, so, which is now part of Schlumberger. They used to be an organisation, so I think we haven't got many more slides. So you'll be, I'm sure, very relieved to know. This is some general comments about system behaviour. If you consider flow rate increasing, you'll find that the pressure drop goes up. And for a multi-phase flow system, as the flow rate increases, you'll find the hold up will go down. The hold up will go down, and the more efficient flow regimes will be promoted, like mist type flows, slug type flows. So in multi-phase flow, the higher the flow rate, the more efficient it is, and the more it relates to single phase flow. That they get closer together as the flow rate gets higher. So that's an important comparison, I think, really. So if you have very low flow rates, multi-phase flow can be incredibly inefficient, very, very inefficient. So that means if you to promote efficient multi-phase flow, if you reduce the diameter of your pipeline, you increase the velocity, and therefore you promote more efficient flow regimes. So the diameter of the pipeline multi-phase flow has another context other than just pressure drop. It's altering your efficiency of your multi-phase flow. So. These are the last set of slides. So, do you want to have a half an hour break?
Yes.
Yeah. Yeah. It's 2.5 hours, so it's heavy going. So. The rooms are, we're okay with the room, aren't we?
Actually, it's up to 12 o'clock.
Maybe we shouldn't stop them. Or maybe have a 15 minutes break. So. Yeah, let's finish this one. Yeah.
So, how much time do you still need?
I'm about halfway through.
The room moved up to 1, sorry, up to 12,
Yeah.
and then from 2 to 3.
Okay, yeah. But what is it used for between those? Yeah. Does it say outside? So carry on.
Yeah.
I'll carry on, yeah.
It's free until 1.
Yeah, maybe we should try and nail it by 1 o'clock. It's gonna be going something. Yeah.
Yes.
So then you can all relax then after that.
Yes, the lecture was booked until 12,
Mm.
but I think we will continue until 1.
If you don't know.
If you don't mind, I'm sure that's fine for the majority. So,
It's like a marathon.
like a marathon. Yes, I already warned them about
If you survive
about
this, yeah, that's
today.
right. You can just survive anything. It's really-
So perhaps we can make a 5-minute break
When?
right now, and then
Okay.
just continue. So just
Yeah, yeah.
5 minutes for you to.
I suppose there isn't a coffee machine around here, is it? Miles away, probably, yeah.
No, we can go and come back. That would
Is it a
be
long way
good.
though?
Not really that much.
Is it in a different building?
Yeah, I live next to the oil lake.
Yes, I mean just here in Housing Chemical Engineering.
Is there a machine?
There is a machine there.
Okay, why not?
So we'll just take a break, 10 minutes break, and then we'll just continue. Okay?
They just go in a discussion, workshop. This workshop, certain groups you have to but still, timetable also mentioned that we have one after Easter. After Easter also there is a mentioned in the timetable. Yeah, even John Packer asked whether we have it that's what we need to know.
Maybe he is already finished. If I go now,
Okay, definitely. Simulate that. You are using water. You need to use a CME. Yeah, in answers itself you have so much environment.
他们就是做一个项目嘛，然后发表了关于
then she saw all your messages.
6月份你们有不是咱们有每年6月份有这个。就是他已经有办，我记得很早之前我们办过。
他的意思是，他的意思是，
这个不知道
한번 히말라야 갔다가 진짜 와, 삼종만에 죽지 않아. 바이킹 코스로 올라갔는데 더 높으니까 후본데 겁나 없어. 자고 일어나서 장르 같은 혼자 누가 같이 플로우 레이트가 급격해지는 거예요. 빨리 프레셔 들어가면 이 속에서 빠를 때 보는데 유속이 빠르네. 근데 유속이 너무 빠르면 프로들이 유속 때 유속 저기 맡아가지고 마이크 사이즈 잘라내고 새로 저런 거 못하나. 그래도 5년 전에 서브시하고 서브시 인스톨레이션하고 그래서 플러그하고 뭐 이런 거를 되게 큰 과제를 해갖고 시작을 했어. 이제 효찬 사업이랑 이래저래 지황에 따라서 일을 진짜 장기 프로젝트를 해야 되거든요. 바로 하시면 되는 게 아니고
딱 느낀 게 그랬잖아. 공지는 알파고 할 때부터 외모인 거예요. 할 때부터 다 누군 거 아니야? 외모 지금 한다고 우리가 따라갈 수 있는 거 같아요.
장기적으로 뭔가 이게 안 좋아서 꾸준히 해야 되는 거 자체하고 온라인에 지금 나중에 먹고 살 거리가
也是为了更新节目的
링업을 해가지고 세계적으로 폼 밀다가 지금 기름값 주문 떨어지니까 the bank is what is the just the bank. All right.
I think I'll bring a flask next time. So.
The break will be between 1 and 2. And then after 2, you'll try to cover most of it before 3, but you have to take more time than some people will go. So, right, so we're going to continue until 1 o'clock, and then from 1 to 2, there will be a break. And after that, we'll resume back from 2 to 3. And I think some of you have a lecture at 3. Is that right or not? Who has a... No? None of you?
Offshore engineering.
Offshore engineering?
Yeah, there is no lecture.
There's no lecture. Oh, perhaps. So in that case, the room is free. So we'll just continue until Nigel finishes.
I'll try and nail it though.
So yes.
Ideally, I'd nail it by 1, but I'm not sure that's possible. Yeah.
Okay, so we'll just.
Is this all being recorded?
Yes, everything will be available in recap, I suppose. Yes, no.
What is recap? Okay, yeah. There's a microphone somewhere, isn't
Yeah, it should have come on the whiteboard.
Okay.
Yes. Well, I have to check because we didn't turn on the computer, so.
The computer's on here, yeah.
Materials will be on Blackboard
But
anyway.
all the materials, these are the ones that you've given John previously?
I can
changed?
PDF them and leave them with you if you
Oh,
like.
yes,
yeah.
that would be great.
Just to make sure you got the most recent. I mean,
Yes.
They're in the same order. That's probably good.
Okay, that's fine.
Which one
So
in the
if
same
you
order,
want,
yeah.
you send them to
Yeah.
me, so I say.
Yeah.
Okay, Nigel, so I think I'm going to go to my office for
Okay,
the second
yeah, no
part.
problem, yeah.
And then I'm not sure if I shall meet you here at 1 to go to lunch together to the courtyard, or
Oh,
you
don't
want
worry
to do
about it.
something else?
Yeah,
Okay.
no, if you want to, yeah.
Okay, so...
I'll ask them where to go, don't worry. Yeah,
Okay,
don't worry about
okay,
it.
so then nice to meet you, and
you,
we'll
yeah,
be
thanks for
in
your
touch
help.
anyway. Thank you very much
Okay,
for
thanks.
everything.
Thank you.
Bye-bye. Perhaps in the future we won't be too busy to...
No, I think I can, as long as you don't mind it being in a day.
No, I think that
I think the
we'll
problem
just
is
continue
if
like
you
that.
spread it over a few days. That's
Yeah,
when it
and I
gets
think
difficult.
perhaps next year what I'm going to try to do is set up it well in advance so we can book the whole group for the whole day.
They'll
And
get
you can
more
take the
breaks,
time
more
or
breaks,
breaks
and,
and then just manage the day as
Yeah, to
find
the
the
problem is
sweet
over.
spot.
Coming back was several times over 3 weeks. Is difficult.
Yeah, no, I understand that.
Yeah.
Yes, I warned the students already since the beginning that they had to sort of take some energy pills today or something like that. But anyway, thank you very much.
Medicate. Yeah.
Okay. See you.
Yeah, okay. So Sharon's leading us for a bit. Well, for the rest, in fact. So. You ready? I'd like to nail it by 1, but I don't think it's possible, to be honest. So unfortunately, I might end up having a break, but we'll see how we go, basically. So far we've only really talked about about pressure. So the other thing is temperature and pressure need to be resolved together, because the fluid properties which affect pressure and pressure hold-up are significantly affected by temperature. So you can't really consider one without the other. Temperature is very important too. Same with oil systems, even outside of multi-phase flow. Just an oil system, temperature is very important because the density of oil is so profoundly affected by temperature. So there's like a whole thing with temperature you need to consider. So when you have a hot product from a well, normally it is pretty hot, typically, because it comes from deep in the earth, which is hot. You flow it through the pipeline. You lose heat, basically. You lose heat will flow out through the coatings, basically. And in fact, there's a simple equation which is the change in internal energy dH per unit length, dH by dL, is proportional to a property of the pipe called U, which is the overall heat transfer coefficient, multiplied by pi by a reference diameter, divided by the mass flow rate, divided by the difference in temperature. So the difference in temperature is driving the loss of heat from the pipe, basically, flowing from the inside to the outside, basically, TA to ambient. And the U is a function of the pipe, basically. A property of the pipe is its overall heat transfer coefficient. The other way you can lose heat is with Joule-Thomson cooling. That's where you expand gas, it gets colder, basically. So two mechanisms: flow to the environment and reduction in temperature due to expansion of gas. So the overall heat transfer coefficient is an important property of a pipe, and it's got three different components. The internal there's an internal component that's often called the boundary layer, and that's where the fluid insulates itself effectively. And then you've got the pipe and its coatings, and you've got the environment. Now, each of these can be dominant depending on the circumstances. For example, if you've got a pipeline manifold on the seabed which has no insulation, it's just bare, you'll find the dominant aspect of the overall heat transfer coefficient will be the internal boundary layer, because the pipeline will be negligible and the environment will be negligible, because it will just be flowing to the environment. So that would be dominant, and that is actually a function of flow rate. If you have a pipe which is pipe in pipe, big heavy insulation, you'll find this bit will be utterly dominant. This will be completely negligible. That will be completely negligible. On the other hand, if you have a buried pipe which is under 2 meters of silt or sand, you'll find this will be the dominant one, this will be negligible, this will be negligible. So it's knowing what to consider when is the important thing here. So the overall heat transfer coefficient is 1 over that, is 1 over internal plus 1 over the pipe plus 1 over environment. So these are the special cases. So free pipe, pipe in a bundle, semi-buried, buried by a berm, basically. So the pipe and its environment contribute towards the overall heat transfer coefficient, which affects the rate in which heat flows out of the pipe. So now you can work it out for the pipe with a very simple equation. Here it is, and that depends on the thermal conductivity of the coating pipe and its coatings. So carbon steel, stainless steel, asphalt, these are different materials you can make pipes of. These are different insulation materials. And sand and mud are obviously things that you'd bury a pipeline with, basically. So in the seabed, because as you probably know, most small diameter pipelines are buried below the seabed. And this is the thermal conductivity. So the higher the number, the easier it is for heat to flow through it. So the lower the number, the better the insulation. So you can see carbon steel is a terrible insulator. Stainless steel is still a terrible insulator, but better than carbon steel. Asphalt may be a reasonable insulator, but it's not very practical to apply in thick coatings. Polyurethane foam is an extremely good insulator, but has no mechanical strength. Sand and mud are actually pretty good as insulators. So you can add all these to this equation for the different layers to calculate your contribution to your overall heat transfer coefficient from the pipe. Soil has an important effect, and again there's an equation you can use to take account of the soil, and that depends on the thermal conductivity of the soil. And there's another little lookup table you can use to work out thermal conductivity of the soil. This is produced by a guy called Kirsten, and he gives us the thermal conductivity of the soil based on the moisture content for sand and clay. So again, I haven't gone into a lot of detail with these, like giving, but there are equations for calculating the overall heat transfer coefficient contribution from the internal boundary layer for laminar and turbulent flow, which are quite complex and in a lot of cases irrelevant or built into a program. So these are all, a lot of these are dimensionless, dimensionless groups. So in terms of the pipe and its coatings, typically, if you want an overall heat transfer coefficient, which is measured in watts per meter squared degrees K, then less than 1 is very hard to achieve. That means a very expensive insulation system, pipe in pipe, some kind of sophisticated insulation system, basically. So, if you need to maintain your product temperature to a very high degree, in other words, you can't go below something which is quite high, then you're talking about big money together. It's typically, bare pipe is about 300. So you can see the difference between heat loss between this and this for the same pipe, same diameter pipe. This is losing heat 300 times more quicker than the other one. So 300 meters of pipe are the equivalent to 1 meter of this pipe in terms of heat loss. Conventional insulation, a couple of inches of something, conventional polyurethane foam, for example, thick polyurethane foam, then you're talking about 2 to 5. So expensive, normal, no, none. So pipe-in-pipe systems have always been a challenge for offshore pipelines. The main reason why is because you have to come up with some way of making up a field joint, some way of joining a pipe-in-pipe system together. And there are different systems by different vendors, with different installation contractors. This is one where they bring the pipe-in-pipe down to one single weld. This is the double pipe lamination system, or DPIS, for Snambajetti. But again, you'll find you could potentially lose a lot of heat in the join here. Second. This is an ITP. This is a proprietary product produced in France by an offshoot of Total, and here they use a screwed connection. They make a weld on the inner pipe, and then they screw the outer pipe together with a threaded connection and sealed connection. Lockstraw Raw is a Danish company. This is the Mallard filter shell. Interpipe. This is the same company, but with ETAP, which stands for East Trough Area Field Production, ETAP. And then some of the systems are actually reeled onto a barge, onto a reel ship as well. So it's possible to provide vacuum insulation for tubing, for example. It's typical. You can buy vacuum tubings where you actually it's a very, very good, very efficient insulation, like a vacuum flask, for example. Where you're separating the inside surface from the outside surface, you don't get any radiation because there's no you only get radiation. You don't get convection or conduction, only radiation. So these are used for insulation systems for cryogenic pipelines like LNG, and for downhole typically. And the Interpipe do use vacuum insulation sometimes as well for their pipe-in-pipe system. So vacuum is one good way. I don't know what that is. Bundles we talked about, hot water flushing going through them. This is a vertical riser bundle. This is for the Girasol project in Angola, and this is a vertical floating unit where they actually heated it effectively. So you can also use conductive heating. This is a flexible pipe, and we could incorporate electrical cables into the flexible pipe to produce heating. So conductive heating, and again inductive heating. Hot water heating again is the other way. This is the Britannia bundle. That's the one I was trying to think of, Britannia, which uses hot water heating. Or you can have combinations as well. So I'm going to skip this slide, I think. Not going into this in detail, but the other thing you need to consider, of course, is stationary cooling, because under a steady state operation of a pipeline, you've got an inlet temperature, say for example that's 100 degrees. The outlet temperature may be 30 degrees under steady state, but the wax appearance temperature may be, for example, 25. So under normal operating conditions, that's fine. Trouble is what happens when you shut down, because that curve will slowly reduce. So it will that temperature will slowly go down. So you've got to consider stationary cooling. What happens when you start up and what happens when you shut down? You've got to consider the dynamics of your field and how you operate it. So, and there are sort of design considerations. For example, as that cools down, obviously hydrates might become an issue. So you'll find that the bits that are below the seabed will cool down much, much slower. So if you can have all your manifolds and pipes sloping, so if you shut down, all the liquid runs down into the seabed bits, below seabed parts, they will stay hotter for longer. So you can actually, by careful design, you can mitigate potential risks from hydrates in a shutdown situation. So this is an example of a buried pipe under a steady state, under a steady operation, under a temperature profile. So this is the big scale. So that's the seabed. This is the pipe under the seabed. This is the bigger scale. That's the sea surface here. This is the pipe. This is the red is 70 degrees. The blue is this light color is 11 degrees. The sea, this is equivalent to the sea temperature, which is 4 degrees basically. So 70, 11, 4. So this is the operating condition. And this is after 5 days. So you shut it down and wait after 5 days. This is using a finite element analysis. You'll see now that the red is 17 degrees. So I happen to know, because I worked on this project, that the hydrate formation temperature is 16 degrees. So because this pipeline's buried, you can actually shut down, and it will be 5 days before the temperature goes down to the temperature below the hydrate formation temperature. So you're using the fact it's buried to mitigate you against hydrates. So if you can design it so all your liquid runs down into that buried bit, that gives you quite a bit of assurance on your shutdown under a shutdown condition. Whereas if this pipeline was exposed, it will cool down literally within hours. Within hours, you potentially get a hydrate problem. So, make sense?
Would there be a case of burying at the last depot on a pipeline that was going to be prototyping?
Yes, you could do. Yeah, I think there's a trade-off between. You could say, well, if I'm burying it half a metre, I don't get quite enough insulation. Therefore, I'd have to add more insulation. Do I invest more money in burying it deeper and avoiding the insulation? So it's a cost construction risk trade-off basically. So then you say, well, how easy is it to bury it to a metre as opposed to half a metre? Or could I even bury it for 1.5 metres? So the construction contract may say, well, it's straightforward soil. There's no expectation of boulders. We've trenched there before. We can easily do 1.5 metres. Then you say, well, okay, we will bury the pipeline to 1.5 metres and not have insulation. So yeah, it's definitely part of a design consideration. So yes, burying intentionally to provide insulation is a very valid consideration. Also, it gives you this as well. Not only does it give you relatively cheap insulation, it gives you this thermal inertia effect as well, to allow you to potentially mitigate against risk when it's shut down. So. That's the last graph, but time related basically. So sometimes high temperature, high pressure pipelines can be quite complicated, because if you can't stop the product cooling down to typically 30 degrees because you get wax in a high temperature reservoir. But the trouble is, if you keep that temperature at 150 degrees, then you get buckling problems. So the ideal situation is you